好。
Okay, okay. Let's quickly summarize the reinforcement learning design for homework 5. But homework 5 is very similar to homework 4 as we just simply extend from 2D space to 3D. Okay, just like I said, if you talk to any people who has experience with reinforcement learning, okay, you will know that reinforcement learning is notorious for its difficulty to train. So unless you carefully design, otherwise it's not that simple. You hit start key, you wait for 1 day or 2 days, and then your agent learn. It's not that case. Everything you have to carefully think about it, carefully design. We already talked about this in the previous week's video. Okay, so today I will just quickly summarize it again using the same schema. So the first thing you need to consider is your state. In this case, we simply extend from the relative position in 2D space to 3D space. Be careful, do not put the parameters here. Think about it, because here we want to learn, we want our agent to learn, oh, what is the best action when my relative position from the goal is this. I don't care my current rotation angle, because during the real test, you never know, because your goal is moving. So you never know where is. So even you have the same rotation angle, for example, your hand is here, but your goal is moving randomly. So the relative position is different. So if you put your rotation angle here, you will confuse your AI, and your AI will not learn. Be careful. Therefore, do remove these three from the code, the example I gave you. Okay, that's the first thing. Secondly is the action. Okay, we have 3 angles in this case. Okay, the first angle, we rotate our base to the right, to the left. Okay, and the second angle, we rotate our arm 1 to forward. Okay, because in this case, when I tested, I found if I rotate my arm 1 backward, it will look strange. That's why here I only allow my arm 1 to rotate forward, and then arm 3 rotate up and down. So in total, we have 2, 1, 2. We have 5 actions here, compared to the 3 actions for the car, where we can move forward, turn right, turn left. So our action is increased from 3 to 5 in this robot arm case. Also, another thing to notice that is in Unity, when you rotate the object, its rotation point is in the middle, in the center of the object. So when you rotate arm 1 directly, your arm 1 will rotate along its center, not rotate at the bottom. That's not what we want. That's why if you look at my scene design, I put an empty object as the pivot point, and the place is empty point at the bottom of the arm 1 or the arm 2. And I rotate the pivot point. And since I put the arm 1 as the child, so if I rotate this pivot point, arm 1 will rotate accordingly. By doing this, the arm 1 or arm 2 will rotate using the bottom as the rotation point. That's what we want. And then the third thing is the reward design. Reward design is very important in reinforcement learning. As in previous video, we already explained the details a lot. So I will quickly, I will skip the details, okay? So basically we consider two types of rewards. First is the event, is sparse. Only when some event happens, then we assign the reward. And the secondly, stepwise. Every step we give this reward. And remember the Kevin's formula? Okay, only when we reach the goal, we give a positive reward. All other rewards are negative. And during the simulation, this reward, the total reward cannot be positive. Okay, means you have to design this number carefully. No matter within your maximum simulation step, your reward will not be positive. Otherwise, your AI will feel lazy and stop learning. Okay, and be careful of these negative values. If the AI receives the negative values, AI receipt is too large, be careful. The AI tends to suicide because he feels no hope. There's no hope in the life. He just suicide. Okay. If the negative reward is not large enough, then the AI will feel lazy because he feel, hey, I work so hard, then I don't get any punishment. Then why I work? So he will circle around. So these numbers, the value of these numbers determine how your AI behaves. So when you train the reinforcement learning, if you see your AI continues to suicide or continues to fool around, watch these values. Then you ask me what is the real answer. Go ask Kevin, Barney, or Carol to see what's their reward design because they succeed. There's just like deep learning, there's no absolute theory for this. Okay, you get the general feeling and then the fourth is the training environment. In our case, I do not put any restriction on the base, so the base can have 0 to 360. And remember, every step I move 0.1 in my design. So in total, I have 3,600 possibilities for theta 1. Similarly, for theta 2 and for theta 3, if you multiply them together, you will find it's about 30 million possibilities for your action grid, compared to the 1,000 for homework 4, the car. It's dramatic increase. From here you can also see that's why we don't want to put these three numbers. Otherwise, okay. And the fourth is the same important as your reward design. So your reward design, the value will determine your AI behavior. Whether your AI going to suicide or be positive or be lazy. Exploration determines how your AI can generalize to every situation. It's like human. Say for example, this Sweden or South Central American company come to Taiwan. They explore. They have some experience with Taiwan. Then next time when people talk about Taiwan, they know. If they do not come to Taiwan, and when people talk to Taiwan, they have no experience. The same thing. You suppose take the car our state is delta x and delta z. If your simulation only allows your AI to explore positive data x, positive data y, negative data x, negative data y, they do not explore these two areas. Then next time when you test your AI, for example, when delta x is positive, means the agent is to the right of the goal. Delta z is negative, means your delta z, your agent is above your goal. Since the AI did not have your neural network does not have any training data here, then you will feel confused. That's why you see your car start to behave randomly here, because you did not have enough exploration here. Or even you have some exploration, but the sample data is not enough for you to build the distribution, then your AI still, because our neural network build the regression model based on this sample. If you don't provide enough training data, then how can it build the regression model? So most of you, if you fail in homework 4, means, oh, I trained, but when I test my AI, it behaves strange. Okay, you understand? It behaves strange. That's why maybe it encountered some situation where it has not explored before. So here we talk about 4 simple design ideas. Of course, if you read the reinforcement learning paper, a lot of paper talks about what is the strategy to make our AI have enough exploration. Okay, so first is the initial state. So here, if you want to train, remember here is our DQN code. If I want to train my AI for an episode, every time we reset our environment have an initial position. So should I start my simulation always from a fixed position, or I randomly place every time when I reset? It's up to you. According to Kevin, for these 2 simple situations, we use fixed position. It's enough the idea is, although we use fixed position, because during the simulation, the AI has the chance to explore all possible situations. And the second one is epsilon greedy, which we have been talking about for several weeks, so I skipped the details. And third one is the maximal steps you allow for each simulation. Means here, okay, when the AI interact with Unity to collect training data, what is the maximum steps we allowed? Based on Kevin, for robot case, he used 20, 40, 48, and for the car case, he used 552. Okay, and finally, is when should we terminate? What is the termination state? This one, I think, if you just copy the class material I gave you to train, then that's why you cannot train. Because in the example I gave you, I terminate the simulation whenever the agent is out of boundary. Consider here. Okay, in the example I gave you, whenever the agent is out of boundary, then I terminate it. I done. I give a negative value and down. So your simulation here, every episode, your simulation terminates quickly. And then look at there, you did not have enough chance. Your AI does not have enough chance to explore the world. Just like if you see a teenager do some bad thing, and you immediately terminate his life, hey, how can he learn something and grow up? You understand? Okay, that's why so what Kevin, he put something at the boundary. So when we detect the AI hit a wall, we do not. Actually, in your code, you did not need to put the wall. You just simply, when out of boundary, we reset instead of done. Okay? Okay. Next thing is the curriculum design, okay? Usually, we start from a simple case, means we place the agent close to the goal. When it learns, then we use the neural network to do transfer learning to place the goal and agent a little bit far away. Same idea applied to robot. The strange thing is here. Although Kevin told me he only do this. He only trained the neural network using an easy case. But then when he tests, in this case, still works, which I cannot explain. Watch here. Taking this example, because your state is delta x and delta y. Okay? So if you train in a simple case, means you sample your training data from this small area. And then if the neural network learns, and then you gradually expand your sample space. That makes sense. So what Kevin says is, okay, I train a neural network using sample data from this small area. Then when I find the data here, means distance is large, then the AI still knows how to perform the action. Here I don't believe. So when you do homework, check this, okay? And then the next one is your neural network design. We already teach how to use torch summary to watch the total number of parameters. And you know the total number of possible states. For example, in a car, we just mentioned, it's about 1,000. But in a robot, that's the search. Okay. So if, here, be careful. If your number of parameters is larger than the total number of possible states, your model will overfitting, because you give a very powerful modeling tool, and your sampling data is small, so your model did not learn the general model. It turns to try to fit every possible data, because your model is much powerful than your training data. So your model does not learn the general model. Instead, it learns an overfitting model. Then, if your model is overfitting, so when the model sees some situation, you will behave strange, because it's overfitting. If the number of parameters of your neural network parameters is much less than the possible number of states, Okay? It's not enough memory to learn. Just like you have a small memory computer and you want to stick a lot of information, it's not able to learn. So be careful to check this number of parameters in your neural network and number of possible states. In Kevin's, for the robot, he used 2 layers, each layer 32 nodes. In a car, he used also 2 layers, but each layer 16 nodes. You might compare. Finally, because we are using DQN, we need to design the memory space and the batch. For the robot, he used the memory size 10 to the power 6, and for car, he used 10 to the power 5. You might compare your design with his. Okay? Okay?